who is Jaikumar Subramanian. He's a senior research scientist at Adobe, India. And he's going to talk to us about sequential decision making in large systems. So he works broadly in the areas of reinforcement learning, single agent, and multi-agent. And he is previously graduated with a dual degree in aerospace from IIT Bombay, and he got his PhD from McGill University. So over to Jaikumar.
Hello. Hello. Hello, everyone. Good morning. First, I wish to thank Professor Shalab and Professor Bhuvan for inviting me here today. And thanks, Aditya, for the kind introduction. So today I'm going to talk about some of the challenges that I have faced in applying reinforcement learning to some of the problems that we face at Adobe. Unfortunately, that data is confidential, so whatever I'll be presenting today is based on publicly available data. But the problems are being abstracted in such a way to mimic the characteristics of real-world data. So there are essentially three parts to my talk today. In the first part, I'll talk about partial observability and the challenges that we face and how we try and handle. The second part is about the multi-agency and how that leads to certain issues which we need to handle. And the final part is like with the advent of Gen AI and both transformers, large language models, diffusion models, how we can now look at newer problems which were out of our scope earlier. So with that, I first look at partial observability. So basically, if you are looking at a problem where a marketer has to sort of interact with a customer, which is a canonical problem that we look at, often the data available is imperfect. So you have like only observations of what interactions you've had with this particular customer in the past. And based on that, you need to decide what is optimal or what is expedient at this particular point in time. The environments, which is essentially the set of customers with whom you are interacting, they are dynamic, their behavior is dynamic, essentially, which means that the transition functions and the reward functions keep changing. The action spaces which are available to the marketer, those keep evolving over time in the sense that you have new products, new schemes, new offers. And often there are other agents in the system which could, so here the customers are also modeled as agents which are not necessarily competitive with respect to the marketer, but you could have competition as well, and you could also have other upstream or downstream agents which affect your ultimate objectives. So this is the overall setup of the problem. And when we look at decision-making problems in the real world, we look at some of the impacts of the problem, the corresponding mathematical frameworks, and then decide whether it is good enough to sort of invest time and resources in solving these problems. So the impact can be considered over multiple dimensions, such as the complexity of the problem currently being solved. Is it relatively straightforward for a human versus like do you wish to automate it? The effect over time, like what is the kind of time available for the effect of the action? Like some actions, such as anything related to branding has got a longer term effect. If it's like a specific offer for a single day or something of that sort, it could be operating over a much shorter time span. The frequency of the actions, how often is the same action being repeated? If it's a very frequent action, then one needs to look at like the resources expended in actually computing the action. If it's very infrequent, it might probably be better to offload it to a human. The monetary impact of the action and other externalities which are not part of the RL objective. For instance, this could be some governing laws and regulations which also need to be taken into account when deciding use of RL in the real world. So some of the frameworks, again, based on some of these complexity criteria can be, ranging from bandits at one end to partially observable stochastic games at the other end, where you consider the full-fledged flavor of, all agents interacting. And what this actually affects in terms.
In practical applications, have you seen anybody use partially observable stochastic games?
In limited cases. So I'll give you one example. But the issue is that when you go to IISd, you are abstracting out some of the complexity. So the action space is no longer practical. So there is also a 2010 IIMAS paper which talks about a game theoretic model for advertisement. And there are several mean field games based work on advertisement, which are like, again, simplifications of this POSG model.
These are actually being used to make this.
They claim in the paper, but like obviously the real world data is not published. So some of the factors that actually affect, like what happens when we look at different mathematical frameworks is that we need to account for the different information structures. That is what data is available about the system at what point in time. The solution definition itself, like from a single agent RL where we look at an optimal policy or a close to optimal policy versus some of the game theoretic constructs where we look at Nash equilibria or refinements of those. Then reliability is a key concern when you look at RL in the real world. Like how reliable can I be that the policy that I'm getting is, in the worst case will not perform worse than the current human policy, even if I don't meet the optimal. And one fundamental question that often is asked is, what is the controllability of the system? Like, can some particular task be achieved? Like someone can request a growth of 30% in the next year using an RL policy, but is it at all feasible? Again, like with absurd numbers, like, 100% growth, one could easily comment on controllability. But even with smaller numbers, it becomes a big challenge. So I think I'll skip this. This was just for setting up of notation. In general, we are looking at a partially observed system. This is the control theoretic framework where we look at observations Y, the actions A, and the noise W. We are only looking at a system where the outputs are observed, and the information state of the system is the entire history of actions and outputs so far. And the policy is a function of the information history, the information state, which is the entire history. And it is trivial to show that this can be considered as a state of the system, even though there may not be a finite dimensional underlying state as is conventional in a POM-DP. The performance and other metrics for the system, the policy, everything is standard as per earlier definition. So I won't go into those notations, but since we now have
Yeah. Your policy is history dependent.
Yes.
Is it because it is a POM?
Yeah, because it is a POM-DP. So we need to look at the entire history. So the traditional approach to handling policies with varying input sizes or histories is to use some kind of a sequence modeling system such as an RNN with LSTMs, GRUs, or transformers. I was having a chat in the morning with Sridhar where he was explaining like some of the theoretical differences between transformers and RNNs. Essentially, transformers limited by the finite context window. So there are some challenges, even though practically we find that they might be more easier to handle. Look forward to Sridhar's talk tomorrow as well to shed some more light on this. But essentially, the math behind RNNs is like more elegant, where you have an internal state machine. So you can show that it is a finite state machine which takes into account the entire history. In transformers, we reduce that to finite memory POM-DP, where the memory is governed by the context length. Another approach which has been common in POM-DP literature is to use the entire history and create some sort of a belief state. So belief state is just a distribution or probability over the states available in the system. So you are sort of uncertain about where you are, but that uncertainty can be quantified using the belief state. An issue with using the belief state in most real world systems is that the state space itself is not well defined. So in such a scenario, it is very, it's not straightforward to use that. And while just plugging everything into a transformer or an RNN seems to be working practically, if we just do that without any additional mathematical constructs, it is very tough to get any theoretical error bounds or properties of this particular system. So essentially what we are doing is studying, looking at optimality over a class of policies. And this class is very large because it is also history dependent. So the question is, can we now somehow reduce this search space? So in order to answer this question, that can you reduce the search space, you need this concept of information state, which is basically a compression of history with some properties such as it is sufficient for evaluating the performance, or essentially in the RL world, sufficient for predicting the current reward, the per step reward, and it is also sufficient to predict itself. So essentially the condition to predict itself can also be replaced by a condition that it evolves in a state-like manner, and it can be used to predict observations. So again, this is well known in history. I'm happy to go into details if it is needed, but it has been shown that with just a single step prediction and sufficient for reward, any compression of history with these properties is good enough as an information state. Often, exact compression is not possible. So we do this approximately, which is pretty straightforward. Like you take the difference of the LHS and RHS, bound that by some particular value, and then you can get approximation errors based on this bound. Again, this is presented in an earlier paper and in several slightly different attempts as well. But this gives a theoretical justification of what one can do with a history and what are the additional regularization constraints, if you will, that you need to add on top of a sequential prediction model in order to reduce the search space for optimality in such problems. So concretely, why is this important? Like if you look at Atari or Mjoko problems, they do not have such a large memory, and for Atari problems, typically you can just stitch together the last 4 frames, convert that to an MDP and solve the problem. So are there real world use cases where you actually need this machinery? So as part of my work with Microsoft Research prior to my stint with Adobe, we looked at this problem of sepsis, use of RL for treatment of sepsis. So it's interesting why we picked this particular problem is that it's very tough to sort of, in general, use RL-based solutions for any healthcare problem because of a lot of confounders with respect to other health conditions. But sepsis is a particular state which is like a quick-acting scenario. So the overall time frame for the operation of sepsis is about 72 hours. And once you start the treatment of sepsis, because it is so serious, it could lead to multi-organ failure. You ignore the prior conditions which led to sepsis. So as such, it is like isolated from other scenarios, and hence this setting is suitable for RL. So again, for sepsis, several data sets are available. This is from the Beth Deaconess Hospital in Boston. So we had like data, which is the EHR data, which is anonymized and made available for general public, which is basically observations in the 72-hour time frame of various vital signs and parameters. And with this, we need to predict like what is essentially there are 2 treatment options given here, vasopressors and fluids to be administered. And we need to sort of predict like what should be the next treatment administration. So this again is a problem which has been well studied primarily because of availability of data and the seriousness of this particular issue. What we try to do with this data is try and answer that is there a sufficiently informative information state or an approximate information state for this problem? And does that lead to better decision making?
Now it is right up to 72 hours.
Yes.
So is it your decision code is 1 hour space?
So we split it into 4 hours, but that was artificial. So some of the limitations of this model are that the observations are not at uniform time intervals. Yeah, those are random intervals, and often they are proportional to the seriousness of the particular situation. But earlier work, like people have worked on this data set and processed it to create a uniform 4-hour interval observation and action samples, because they wanted to fit it within the MDP or POMDP framework and not go to the event-driven framework. So essentially to avoid any semi-Markovian nature. So as I said, like this problem has been attempted by several people in the past, taking several shots at how to estimate an information state, how to create a state representation, what are the observational variables to include, what are the things that you can sort of avoid. Again, all these are available in various papers, including the reference cited below. So I don't want to get into the details of this specific problem, but I want to focus on what are the issues. So first of all, you can come up with very different architectures. So the first one is a simple RNN-based architecture, which looks at predicting the next observation given the entire history. Or you could look at the work that I presented on approximate information state, which predicts, in addition to the next observation, one could also predict the reward, but with the addition of the particular action. Again, slight changes in terms of what are the inputs lead to various dynamical models. And what we did was use these various models, created state representations. I mean, in hindsight, now I would have used UMAP to do this, but we used PCA to actually compress the higher dimensional representations into 2D. And here the red and the blue symbols stand for patients who were ultimately, were in the non-recoverable state and patients who are in the recoverable state. And we tried to see whether our particular state learning or this state representation clearly separates the two. So we found that in some of the methods, those are clearly separable. Some of the methods, those aren't in this particular 2D projection. But this is not conclusive because of several errors involved in the process, like you are doing a 2D reduction, which is not strictly necessary other than for human explainability and things of that sort. So this was not a conclusive test, but it still showed that these various slight differences in the architecture can lead to differences in representations, which are not obvious as to what their impact can be. So when we use these various representations to actually look at prediction of the next observation, we found that the accuracies were fairly were within the acceptable range. So it's not that there was one particular method which like stood out over the other, but that did not translate to performance in the actual learning. So when we use an offline algorithm, which was a batch constrained Q learning algorithm in this particular case, we found that there are some methods which do much better than the others. Again, this begs for more research and investigation into why this happens, in addition to the inherent noise within these learning algorithms. But the spread between these various methods indicate that there are some different dynamical characteristics of these methods which need to be explored, which is just beyond like the simple next step prediction. Again, we tried this with various hyperparameters for specific algorithms. And this is also a bit of a challenge, because what we actually did was try to vary what are the observations that we are trying to predict. So you don't want to predict every observation that you are measuring. You only want to predict observations that are in some sense controllable. For instance, if there are some observations that vary in a random manner or are not sensitive to this particular input of either vasopressors or fluids that you're administering, then you don't want that to be part. For instance, like weight, should predicted weight be a part of the predictions or no? These kinds of questions, when we asked and we tried to do variations, we found that that also led to significant gap in terms of performance of the same algorithm. So this again, like also across algorithms leads to a large difference. So again, like the conclusion that one can draw from here is that whenever you are working with real world data, with partially observed data, it's not clear as to which method works best, what sort of hyperparameters, and you need to design various downstream tests. So in this particular case, what we were planning to do was to use data from one hospital to now investigate performance in some other hospital and to see actually what translates well. So this brings me to the end of the representation using sequence modeling part for history compression for the purpose of RL. So where we looked at some of the challenges of partial observability. Some of the things that even these methods cannot handle is missing data. Non-homogeneous data, for instance, about different patients, you can have different data. We noticed that electronic health records also often have a lot of annotations by doctors and nurses, which we ignored for the purpose of our analysis because we did not know how to incorporate that. So those were the limitations. I'll again come back to how can we handle some of those limitations towards the last part of my talk. But this again begs the question, with the advent of modern methods such as modern architectures such as transformers, can we do the same thing using transformers? Are transformers a drop-in replacements for LSTMs or GRUs? So some of the initial work with transformers as drop-in replacements led to a lot of stability issues. Typically, they were not as large models as the LLMs you see today. So initial applications weren't too successful. Then people started going to larger and larger transformers and looking at essentially just the sequential prediction part. So initially people were looking like, should a transformer be considered as a policy? Should it be considered as a state representation mechanism? Should it be considered as the backbone of a network which predicts both the actor as well as the critic? So various things have been tried in the past, including nowadays where they say that a single transformer can be the world model as well as the policy rolled into one. And with the advent of upside down RL as well, like several things have been investigated here. And there is again no clear consensus as to which works better. Most of the results are in the domains of Atari and Mujoko, which do not challenge as much as the real world problems because of lack of stochasticity and also because of lack of any long memory kind of phenomena there. So what we decided to do was we looked at all this literature and we decided, let us first ask the question that if we use something like decision transformers, wherein they just model the sequence in an upside down RL fashion, and we just somehow get trajectory encodings from these transformers. So basically fine tune any particular, say, transformer using just data from trajectories of an expert. So use some other RL algorithm, learn an expert policy, encode the expert policy using a transformer, get the encodings and see, are these encodings clusterable into different unique clusters with different behaviors. So our first question was like, do transformers represent trajectories with specific behaviors in different clusters? And we found that the answer is yes to this particular question. Again, for simple games, this is basically just the most obvious methodology. We just got.
So you couldn't use the transformers with the offline data to learn the policy.
Yes.
You do some other RL data to learn the expert policy or something.
Yes.
And then you somehow.
So I already had an expert policy. Yeah. And what I wanted to know is that if the transformer is able to clone the behavior of this policy. Yeah. Because I wanted to avoid the stability issues with training a transformer on RL. So this was a more basic question that we are just doing behavior cloning, something which we know transformers are good at or have been proven to work well. But do these transformers representations, which is the penultimate layer encodings, do they carry some meaning? So that was a question that we wanted answered. Again, the devil is in the details here. Like if you have a 1024 context length transformer, it will give you an output of the size of 1024 embeddings. Now you need to combine these embeddings in such a way that, as Sridhar was mentioning, you need to take into account the sequence position as well. So it should not be permutation invariant. if you do any kind of conventional approach, like just summing things up or, just taking the mean of all these embeddings, it becomes permutation invariant. With the slight hack that because we use positional encodings for the transformers, we are hoping that those positional encodings take into account the impact of the particular position. But again, the jury is out here, like what is the best way to combine and get a single representation for a trajectory. So some of the other methods used in the NLP literature is to have a separate, a separate token or encoding for this entire sequence. But there has to be an associated downstream task with respect to that particular encoding. Since we didn't have that, we just combine the encodings of the entire individual tokens within the trajectory. The rest of the algorithm is simple, that we just took these policies, clustered, and then in order to make it, in order to see whether this can be used for explaining decision making, we try to get the Shapley value of particular clusters in decision making. And we found that in simple problems such as very simple grid walls or Atari and Mujoko problems, these seem to give explanations which are also very human interpretable. So if there are no questions here, I would like to go to the next part where we deal with multiple agents. And in the end, I'll try to bring all of these together. So the issue with multiple agents is that often we are dealing in environments where you do not have this isolated treatment like sepsis, where you are now a doctor treating a single patient. But consider the case like COVID, where there is an epidemic and you're treating a population of agents, but the agents also interact with each other. So a good framework for these kinds of problems is called an agent-based model, where you model each individual agent either as an automaton or as a learning agent. Explicitly model the interactions between the agents, which leads to downstream effect, which are often non-obvious. So this is known right from the time of Schelling with his model in terms of racial segregation of housing and various such phenomena. But more recently, this has been used in various simulators for training self-driving cars, and also in predicting things such as the spread of the Great Recession, which started off in a localized region as singular defaults, which should have been contained locally, but because of the interconnectedness of the system, it's led to something which was larger and global. So mathematically, this is because of noise amplification in a complex system. So small perturbations can also, in the right place, can also be magnified to lead to large perturbations in the entire system. And normally, smooth differential equations based models are not equipped to handle this. So several conventional macroeconomic models actually model such phenomena by adding external constructs called shocks. So what was shown in this paper by Stiglitz and his co-authors is that using agent-based models, you don't need any other external construct, and you could still simulate such a contagion. So this broadly applies to opinion dynamics, hence the world of marketing and what all I work on. But again, for the purpose of looking at how do various mathematical methods work in this, we picked the problem of COVID spread. Again, primarily because data is publicly available. Lots of researchers have worked on it, and it gives a nice comparative platform. So these are some of the advantages of using agent-based models over conventional SIR, SEIR, or any of the various compartmental models, as they call. Again, not going into details of these comparisons, but happy to discuss if needed. But what we look at is essentially all this boils down to, can we predict the behavior of a user, or in COVID, can we predict the behavior of each individual person who is susceptible to the disease? Can we capture networks of these user interactions? And can we look at all available products and services, which in this particular case of COVID could be various testing vaccination strategies where people have volition in terms of deciding whether to get themselves tested, whether to get themselves vaccinated or not. How do they make these choices, and how the availability of these options within a system affects the overall state of the system. Now to answer your question, which you had asked earlier about, have these ever been used in practice in a marketing scenario? So there is a 2010 paper in IISc which talks of a phenomenon called as lock-in effect. So to illustrate this, I'll just take a case study of VHS versus beta. This is very old for people in this audience to sort of know, but earlier when video cassette recorders were popular, there were two technologies, VHS and beta. Beta was by Sony and VHS was by a consortium headed by Philips. In terms of technology, like beta was the first mover. Quality, most professionals felt that beta was better. Price was almost similar. And based on this, one would presume that beta would at least have 50% of the market share or a respectable portion. But what actually happened was VHS completely dominated the market, with beta not having any share, except amongst a small group of professionals. So actually what led to this was basically change in behavior of people as a result of advent of this technology. So when this recording technology was launched, it was primarily used as a time delay mechanism. So can you record a program that you wanted to see and see it later? But a consequence of this was now you could record content and make it available for distribution on a much larger scale. So this led to the advent of video circulating libraries. So that connected these various individual users which were disconnected, and then led to a platform effect. So there, the first mover, like initially VHS flooded the market with a lot of recorders and initial, VHS tapes. So that sort of influenced, downstream purchase decisions by other people, which led to VHS dominating the market. So the critical mass for which you need to initially capture to ensure that this particular lock-in happens depends on the specifics of that system, and this phenomenon is called the lock-in effect. So in this 2010 paper, Garlick and Schlee actually looked at this particular effect, simulated this in terms of advertising in a grid world, and showed that once lock-in is attained, unless and until you do a serious change in terms of significant additional investment in advertisement or a product change, it's tough to break out of that lock-in using smaller investments. So if this research was done in 2010, it begs the question as to why it has not been used, since then. So there were three primary limitations. One is scale. So this was the era when agent-based models were simulated using a software called NetLogo. So it does not scale very well. So this is typically, you had grid world type agents. So this is done on a 30 cross 30 to 100 cross 100 kind of grid, all the experiments, which puts a cap on the maximum number of agents. The second issue was the speed with which you can compute these things and the complexity which you can input. So typical decisions were binary. So you can look at duopoly, but most real world scenarios are more complex than that. And the final issue is like one couldn't calibrate these models to real world data. So these models were never grounded. And one of the positives of this model itself is that it is able to predict non-obvious phenomena, which are also sometimes called emergent phenomena from initial input, which is an advantage, also leads to a big problem in calibration. Now you cannot easily decide like what should have been the inputs to actually match this generated output. So these are three primary challenges which led to a delay in the deployment of these models in the real world, which is what we decided to look at. And the main approach to actually solving these problems for us was to reformulate this using tensor calculus and modern deep learning inspired tools. So essentially, once you write this in terms of tensor algebra, you get scalability. You can use modern accelerators. And if you're a bit careful in writing the transition functions and the state evolution equations, in order to ensure that they are either differentiable or like close analogs of differentiable functions, you get AutoGrad for free. So the advantage of that AutoGrad for free is that now you can calibrate these models using ground truth observed data, thereby leading to the grounding of even agent-based models.
Can you just tell us a little bit about at the micro level, what exactly are the agents doing? What dynamics are available to them?
Yes.
Playing a game?
So they are not playing a game yet. So what the agents are doing in a nutshell is actually interacting with other agents. So basically there is an interaction graph. The interaction graph can be static or dynamic. So it could be dynamic based on the occupations of the agents and where they interact geographically. The interaction graph leads to an accumulation of interactions with the neighbors. And then there is a stochastic function which takes this net interaction and determines infection or not. So essentially R0 is the infectiousness of this particular infection for each interaction. This sort of aggregates R0 over all possible interactions over time. So that is what the agent does. In addition to the interactions, the agents also have an option to get themselves to quarantine themselves, which sort of removes them from the interaction graph, to get themselves vaccinated, and to also test themselves. So things like there were questions about RT-PCR versus say the quick antigen-based testing, and the question was like which is better from a population perspective. So an agent-based analysis, in fact, using the model that we developed, also we found that because of the quick response of the antigen test, even though its accuracy is poorer, it can lead to reduced spread compared to the RT-PCR with a higher accuracy, which takes 3 days turnaround time. So some of these are the kinds of lower level questions that we attempt to answer, and these are the lower level questions.
You assign rules to each agent. That agent looks at the interactions.
Yes.
Looks at the cost.
So these rules are in the form of policies. So these policies can be made learnable, like if you want them to, but then you may need to assign some objective for the agent as well, which we did not do. But these rules are essentially in the form of differentiable policies. Yeah. Yeah.
So when you say that the local agents through their mind, or they actually directly have access to the state of the other agent?
So they don't have access to the state of the other agent. Their interactions can be both direct and indirect. So direct interactions are when two agents meet each other. The indirect interactions are like agents affect the availability of vaccine. So if one agent consumes, say, a vaccine dose, then the availability of vaccine for the other agents goes down. So which is often termed in population biology as stigmergy. So both these forms of interactions are possible.
And are they completely independent or collaboration?
So their objective is sort of global in terms of like preventing overall spread. One could give them individual objectives as to if you assign. So some people post this work have also assigned economic incentives. So for instance, like one could quarantine and reduce the spread of infection, but that would lead to a loss of income for that particular agent. If you start modeling those aspects, then these agents become like sort of mixed competitive, cooperative kind of. But cooperative is the easier part. The one with the competition leads to lot of instability in the system.
How many agents have you got?
So initially we had 1 million agents. Then now we went to like the level of an entire state in the US for which data was available. So this is horizontally scalable because so essentially like we went from NetLogo to PyTorch. So initially with JAX and then with PyTorch. Now those take care of the scaling. So you can now take these because code written in this can be easily transferred to accelerators like GPUs, TPUs. They permit horizontal scaling. And here we are still talking about everything synchronous. If we try to get into the async part, we'll get like a better latency along with throughput.
Say it was every agent in conjunction at that time, at that particular time.
So basically, I don't do a state update till all agents have acted. So instead of say in the linear algebra world, I'm looking at Gauss-Jordan rather than Gauss-Seidel systems.
So now, whether you say rule-based or policy-based, agents are using simple criteria for deciding what to do. They're not
Yes.
solving a complicated mathematical problem. They're not solving a
No, they are not solving a complicated mathematical problem. They may try to optimize their local objective using RL, which we did in some scenarios like opinion dynamics and all. So for instance, like in opinion dynamics or say in logistics, you have a particular scenario where you have say a time for which like a time within which you need a particular good, or you need a quality of the good that you are actually purchasing. So that will lead to a local reward function which you need to optimize. Now your policy just needs to be complicated enough to process your inputs to produce a distribution over your chosen actions. But it does not need to account for the knowledge of the entire system. One agent need not know that there are, you know, a million agents in the system and things of that sort. So again, in the interest of time, I'll sort of skip the details, but questions such as like, you know, what will happen when you delay a second dose of vaccination at a system level? Those are questions that are, you know, better answered using agent-based models. And it's not just our work. There are like multiple papers in this, like at least 10 or 15 papers by different research groups on this particular problem itself. The only thing that we brought to the table was make it differentiable to connect it to, you know, ground truth data. Again, there are other ways of like connecting it to ground truth data through careful calibration. But our objective was not epidemiology. We wanted to like bring it to marketing where this approach makes more sense. And how do we take it to like sort of a more general framework where each agent acts with its own objectives? Is we take this kind of, so simple thing here is to do is assume the all the agents that are not the marketer agent or not the government agent to be part of the environment. So their behavior is static, and you say the environment is static, and you use standard single agent RL here, albeit the spaces are pretty large. Or you could assume the environment to be dynamic, but not strategic, in the sense it's evolving, but evolving slowly over time. Again, the same methods work, but the learning has to be done continuously. But what is more interesting is, can we now decouple, can we now take that to a multi-agent RL problem? So some of the challenges in multi-agent RL, while you know, it's tough to cover all the challenges in the short, short period, but like the key essence is any MARL algorithm, the difference over any multi-single agent RL algorithm is it sort of tries to decouple the agents using some other object. So this is the key idea. So when you have like two agents as is there in the, you know, the left part of the graph, there are algorithms where one agent has got an explicit model of its opponent, thereby decoupling it from the actual opponent. So you reason versus this explicit model. Then there are some intermediate algorithms again, like which claim to work over a series of agent populations from 2 to a few numbers. But again, these do not, so typically 10, 15 agents are kind of the limit for such algorithms, because then practical constraints start becoming very high. Solution concepts, they are more ill-defined in such kind of systems. So if over the more than 2, if you want to look at the competitive case or the cooperative case towards, you know, fairly large number of agents, the next area where we have some kind of control is where you're dealing with populations. So because there are an infinite number of agents, you go to standard mean field theory from physics, and you say that each individual agent is small enough, is so small that it cannot affect the entire population. And it can, the mean field itself becomes a decoupling object between, you know, the various agents. So in epidemiology, in marketing, in like various such industries, when there is a single major agent or a few major agents and a larger number of minor agents who have less control over the system, this sort of framework works best, which can now be plugged into an MARL algorithm. So you have like multiple agents interacting with the environment, and you have principal agent also interacting with the environment. And you're more concerned about the principal agent's policy, and all the other individual agents, you are offloading them to have either identical or a small class of policies, which can be easily trained. Again, the issue here is the solution concept, like what kind of equilibria are you looking for? That will determine the information structure, what kind of inputs that we need for the policies of the different agents, and ultimately like how stable that learning framework is. So I'm almost at time. I'll take like a few minutes more to now talk about the final aspect of some of the limitations of RL that I wanted to cover for applying in the real world. So all this is fine with idealized actions. For the sepsis problem, we actually decompose the action space into discrete 25 actions, so which made the analysis fairly easy. For the agent-based model that we spoke about, again, the action spaces were discrete, whether you take vaccination or no, even though it was like fairly large, the actions themselves were not high dimensional. Subsequently, like we also didn't handle things like in opinion dynamics, we say that an opinion is spread amongst a student, amongst a population, and the opinion is either positive or negative. But in the real world, you often have rich content, like you have emails, you have images that are being seen. And with the advent of generative AI, people are asking the questions that can you use these images directly? And can you now generate actions like predict which images can lead to what kind of response? Or you look at reinforcement learning problems where you have goods to recommend, offers to recommend. Can you create new offers? Can you evaluate new offers without having the restriction that those offers or similar offers need to have been seen in the past? So we want to try to avoid the cold start problem. We want to have a universal language or universal embedding space for the actions where new actions get added to the same space. So prior to this, there was a lot of work on like, can one, using the state space, assuming the state space doesn't change or the observations doesn't change, you can now represent action in terms of the transformation matrices. So each action will have a transition matrix, which will take you from one set of states to another set of states. And if you can encode this transition matrix or the space of all these transition matrices, this will form a universal encoding space for the actions. So some papers investigated this idea, but the issue here is that even the state spaces are ill-defined in most real-world problems, and the observation spaces often grow with time. So one solution which we found, again, empirically to work well is take a problem such as say, football, which displays enough complexity in terms of the fact that each agent requires complex strategy. It is a multi-agent problem with sparse rewards. And it also has partial observability that each agent has got only a view of a limited view of the agents around that particular agent. And we found that if we simply take this problem, use a large language model to solve this problem with a few tricks based on observations from robotics, that LLM performs very well. So including things like if you want to add domain knowledge. So can you add domain knowledge to this LLM, which is not from this particular game? We also found that adding such additional domain knowledge helps in learning. If you arbitrarily mask out some observations, because LLMs essentially learn to complete sequences, it can handle partial observations, it can handle incomplete observations pretty well. So some of the problems that we noted when we were looking at sepsis, that the observations are not homogeneous across patients, and we artificially dropped some observations to make it homogeneous. We need not do that if we are able to use an LLM well. And also sometimes when we have additional data like annotations in the electronic health records, which are often in the form of language, those can be incorporated more easily in this kind of system.
Can you describe more about how the LLM is being used? Does each agent here use an LLM for a policy, or what is being used?
So basically here, like we pick a single ego agent, and that agent uses a policy to, we are actually training that agent's policy using an LLM. The other agents are part of the environment, which are considered static for the moment.
This is the LLM generated picture, right?
No, this picture is not LLM generated. So this is like just a language modality. So what we do is like we convert this picture into English. So basically an English language description. So within the context length of the LLM, which like you get a few thousand tokens in any case.
How difficult is it to create a picture like this? Each agent is trained, they look at the environment, they decide the next moves, so on and so forth.
With current models, doesn't seem to be that difficult, but we haven't experimented with those.
Essentially, the cost is being given and because of actually form and they learn from
Yes.
part of the all the generate.
So basically you can, so here like, so this is Google Research Football environment, which is like a publicly available environment. You can sort of run as many policies as you want on this environment, generate additional training data and use that. So we did it in a batch mode, like not pure offline.
But the end of the day, it's just actually how it's put it.
So sequence of observations and actions. In this case, also the rewards where you scored or no, where the goal difference becomes the reward. And the specific method which we used here was upside down RL, inspired by decision transformers. And the inference we did was using an approach called SECAN from the robotics literature, which allowed us to prevent any hallucinations.
In future, each one of us can train our own players on the software and get them together and have a game on the virtual game. Right?
Yes, but here again, the caveat is that this is not a pure MARL algorithm. So here, this agent assumes that the other agents are fixed, and you can like change the difficulty level of the environment. But
maybe in 5 years, 10 years.
Sure, I mean, people are already working on several such extensions. So
There is a crowd of people who come to watch the game virtually.
yeah.
All of that can happen, right? And the people better.
I don't know about that part, but what definitely people are investigating now is football commentary. Can you use that now, not just for learning to play games, but also in training? So can you now use these kinds of models to form assistive devices in training for, college football and things of that sort? Yeah.
Right, then
So this is open source. Base model is open source. This was a 1B model, but if you use something like Mistral or like say Llama 2, you will get better results. But again, the problem is like most of these RL. So the thing is we beat PPO, but like we use much more compute and energy than PPO. So if you ask me like for this particular problem, like would I recommend using an LLM? No. But this is just like proof of concept and like, we need something with public data to actually sort of, compare with earlier methods and like sort of publish as well. So we look at all these traditional RL environments. There are few text-based RL environments that are like being developed now with some baselines. It'll be interesting to see these algorithms perform on those. But as such, as of few months ago, like there aren't any clear environments for this. So we do beat PPO here, but with like much larger compute. Like if you give the same compute to PPO, it might like do much better. So then the final part is like can you now do RL with diffusion models? So diffusion models with LLMs in the pipeline, and this is again pretty straightforward in terms of concept. Mainly, it is what is surprising is the stability of these models to RL. So from traditional RL, like deep RL literature, we know that these models are very fickle. But some of the things that we have observed is that when you go to some of the state-of-the-art diffusion models, because here what I'm showing is the results using stable diffusion. So what you see like from top to bottom is we look at like performance data of these various images, say using Twitter and other publicly available data sources, where you look at like, can you now see, can you now generate images which are likely to get more engagement? And we find that typically it is fairly easy for these models to evolve. What is again not clear here is what should be the evaluation benchmarks. So typically these lead to like sort of A/B testing, qualitative studies, and those kinds of effort, which are not scalable. again, the standard of offline of policy RL evaluation challenges are much more exacerbated here. But what is addressed is the fact that now we can deal with images as an action space. So that really scales out the algorithm, and putting these three together, we can now at least think of how can you handle the marketing problem on the whole as a comprehensive RL problem, and can you now then come up with marketing strategies. So that was my.
We'll have about 4 minutes for questions. Please feel free.
Yeah, I just wanted to ask the one example that you gave. You said that you converted the frames to an English language.
Yeah.
And then you did some training on it. Would you like please touch upon how did you do that exact thing, or is it proprietary?
No, this is all publicly available. So right now you have tools which will actually give you description from a frame to a caption. So again, like this is not yet utilizing the full power. So some of the things that we are still investigating is that if you use the synonym of a frame, right, you change the language, you still get the same performance, or is it just blindly following that particular pattern? But verbalizing these images is again like open source standard available things.
It's basically you did like what would conventionally be done by CNN.
Yeah.
Into like obviously games.
Yes.
You did it with a kind of a model that converts it into English language and get your policies.
Yeah. The challenge here is not the conversion from, say, any modality to language. And with the advent of like LMMs, large multimodal models, you don't even need to do that. Right. So basically, you have a transformer-based architecture as the backbone. You take like any complex input that you want. The question is like, can you do RL on top of this? And with conventional algorithms. But this part where you're bringing everything to, say, a homogeneous domain, that has been solved in the last couple of years. So you have like Blip2, which is one of the more popular models where you feed an image, it generates a caption for the image. Similarly, you can feed like small videos, get description for the videos, where it does a frame by frame partitioning of the video and things of that sort. And you have the other way around also, give textual description, it creates an image.
In the sepsis problem, is there a lack of bad actions and their impacts? And if so, does that person expect anything?
It's tough to answer. There is a full coverage of the action space. Are there bad actions is tough to answer. So the first paper that that worked on this was called AI Clinician. It was published in Nature. So there they sort of said that the policy that was derived, assuming this was an MDP, matched with the expert physician's policy. So they sort of said that there were no bad actions. But then once you get into the details, there are so many assumptions made. And one doesn't know the impact of these assumptions on the optimal policy. And sepsis is not such a well-studied disease in terms of how it progresses in a fundamental way. So one cannot answer this question. But are there bad actions taken? There would be, because we have reduced the state and action space into such a small set that coverage we get. But with the advent of like, again, the modern tools, we don't need to do these kinds of compressions.
So it's how it should make this by making 50% by itself.
So one is a traditional approach where you use PPO or something. So you can add a value head, which has been followed by some people. And then so essentially just consider the LLM as the backbone, like an RNN with a value and a policy head.
They also use LLM as just translator, like to translate in the code and to translate like. And after that, that coder, their agent coder codes that thing and goes to the map, which help them. So, is it possible to like avoid that process and make LLM itself to create objective functions?
I mean, the short answer is we don't know. I mean, right now the abilities or the limits of the abilities of the LLMs are not known. So for instance, like there is a paper called React, which actually sort of says that you can do entire RL only via prompt tuning. So basically, there are three ways to use an LLM for RL. So you play with the prompt space, you play with the weight space, or you add an external adapter. So the external adapter is the most grounded way and the easiest way if you want to like, sort of ensure, some kind of performance. So which is why we went to the external adapter space, which was a SECAN based approach. The other two approaches are like you tune the weights of the LLM itself to sort of fine tune the LLM or RLHF the LLM to do RL, or you play in the prompt space itself. Now, each of these three spaces has each of these three class of methods has got different controllability, right? Not everything can be achieved using each of these, but we do not know the limits. So as of now, I do not know whether one particular class of methods is more promising vis-a-vis another.
Okay. So I suggest you take other questions offline because we are out of time. But let's thank the speaker again.